everyone. Thank you for attending the session, even though the timings have changed. Today we have Ziliang Zhang from University of Bristol. He's a PhD candidate there, and today he'll be talking about multi-hazard probabilistic assessment of healthy and aging monopiles supporting offshore wind turbines. Thank you, Ziliang, for your time and presenting, and it's all yours now.
Yeah, thanks very much. So, all right. So before we get started, here is a list of contents you can expect. So we'll start off with an introduction to our research background. Before then, we move on to the main section of our talk today, which is a dual intensity measure cloud-based fragility assessment. So we'll be going through both the numerical modeling aspects, and we will then examine the impact of using different regression methods as well as different intensity measures to the final derived fragility functions. And after that, we'll be looking at a very quick example for aging offshore wind turbines. And then finally, we'll be closing our discussion with a few words of comments. So the motivation of our work can be explained really by our title of the talk today, which is the multi-hazard probabilistic assessment of healthy and aging monopile-supported offshore wind turbines. So as we know, wind energy is being currently considered as a major driver to transition from conventional power assets to renewable. So the figure on the left-hand side here provides a comparison of investments between offshore and onshore wind turbines. So you can see that proportion of the offshore wind turbines is really significant over the recent years. On the right-hand side there, we may see that despite this increased investments on offshore winds, its overall growth in terms of its new annual installation is still pretty low. So the reason is that the offshore wind is currently not as quite equally cost effective as compared to those, for example, fossil fuels, to nuclear power, or to even to onshore wind. On the other hand, the industry, or rather the policy, is now committing to offshore wind for very good reasons. So from only an engineering point of view today, the technical benefits mainly include the fact that the offshore wind turbines have access to more stable wind direction and wind speed, and they also have access to larger installation spaces. So secondly, the reason why monopile-supported wind turbines were of interest was because that the foundation type is simple and robust, and it has lower costs, so it helps to enhance the cost efficiency and the robustness of the overall offshore wind energy industry, let's say. So also being the most popular typology of foundation for past and recent offshore wind turbines, it is really expected to remain in service for many years to come. So the third keyword is healthy and aging. Given the fact that the operation and maintenance plays a really important role to the overall cost of wind energy production, and that the supporting structure of wind turbine is most likely to be to remain valuable even approaching the end of the turbine's design life. So it is now quite common for the owners to consider for both mechanical refurbishment and lifetime extension for their units. So given this, the key questions are how to reassess structural performance and how to characterize previously undetermined hazards for these aging units. So that leads us to the fourth keyword here, which is probabilistic assessment. So naturally, large uncertainties exist in multiple aspects of this problem, including site conditions, multiple loads, and structural properties. So taking wind load, for example, these figures here show several different levels of uncertainties associated to wind. So here is the variability of wind directions. Here is variability of the average wind speed at a given site. And there is also the variation of this annual mean wind speed, which is different over different years. And the final keyword here is multi-hazard. The term multi-hazard here mainly refers to combination of loads associated to the wind and those introduced by earthquakes. So the reasoning behind the necessity of adding seismic actions into our consideration is demonstrated through these comparisons. So historically, the offshore wind turbines were mostly erected in areas with low seismicity. But for today and future, we'll definitely be seeing areas with high seismicity as well. And second, the capacity, therefore the size of the wind turbine of today's is potentially doubling or even tripling these wind turbines from around 10 to 15 years ago. And thirdly, probably most importantly, the existing offshore wind turbine design codes have all suggested the response spectrum analysis method for seismic design. So as we all know that the response spectrum analysis method is first of all a linear-based approach. And besides, even if the wind turbine is intended to be is designed to be fully elastic during its entire service time, the response spectrum analysis method might still be, let's say, insufficient because it does not have the ability to consider any of the dynamics that happens above the supporting tower of the wind turbine. Therefore, the old seismic design methodology is probably now outdated from our consideration. And it is also very important to note that contrary to some of other engineering problems where different hazards might be okay to examine separately, in case of our offshore wind turbines, a multi-hazard framework is quite essential. So a number of previous studies have shown that depending on whether these hazards are assessed independently or jointly, well, a significant difference can be found in the predicted structural demands, let's say. So this has been proven both numerically and experimentally. Also, offshore wind turbines were found to be vulnerable to some specific types of earthquakes or ground motions. So these include vertical ground motions, pulsar ground motions, as well as crystal and interface types of earthquakes. So given all of these considerations, the best way of assessing this problem we thought would be to use this dual intensity measure fragility assessment framework. So basically it is an extrapolation of knowledge from previous studies involving conventional reinforced concrete structures as well as bridges, where the two intensity measures have been specified for either the same phenomenon or for different hazards. So now, for the main part of this talk, let's start with the numerical modeling of the wind turbine in OpenSees. So for that, we need to first understand the properties of this wind turbine that we've been using in our study. So this wind turbine design was developed by the Research Institute of the US National Renewable Energy Laboratory, NREL. And its full design details are available to the public online. Therefore, you can really see this, this wind turbine has been used in many of the previous studies. So the typology of this wind turbine is what is called a classic Danish configuration. So basically every single modern wind turbine is in this configuration. So it is a horizontal axis, three-bladed, upwind, and variable rotation speed, pitch-controlled wind turbine. So the responses of the wind turbine is directly defined by its typology, obviously. And firstly, we've been looking at these steady-state responses. There are three key wind speeds that define the boundaries of different stages of behavior of the wind turbine. So there's the cut-in wind speed at 3 meters per second, the rated wind speed at 11.4, and the cutout wind speed at 25. So in this range, the turbine will be operational. When the wind speed is below 11.4, the blades will not be pitched, and the rotation speed of the turbine will increase from around 7.5 RPM to around 12.1 RPM, which is the rated rotation speed of the turbine. And consequently, the forces felt at the top of the tower by the wind turbine will increase from around 200 to around 800. On the other hand, when the wind speed is larger than 11.4, the pitch control mechanism of the wind turbine will be engaged this time, and the pitch of the blades will be adjusted according to the real-time inflow wind speed. This is to maintain a constant rotation speed of the turbine, therefore to regulate the power generation process. And at the same time, this time, the total rotor thrust will be decreasing monotonically from around 800 to 400. So this is basically what makes a wind turbine very different from any of the ordinary structures subjected to wind load, because the structure this time is active on its own. And the typology of the wind turbine also defines its modal response. Here it is a Campbell diagram of the wind turbine. So in rotor dynamics, a Campbell diagram describes eigenfrequencies as a function of the rotor's oscillation regime. So these colored lines here represent the natural frequencies of the structure for different modes, whereas the black inclined lines represent the rotor frequency and its overtones. So the rotor frequencies are expressed in both of these axes, one in the unit of hertz, the other in the unit of RPM. So basically they are the same thing, just expressed in different units. The two most important rotor frequencies are called the 1P frequency and the 3P frequency. So this is the rotor frequency, and the 3P is the blade passing frequency. These frequencies must be avoided. And for the wind turbine, which is a typical wind turbine herein, for our NREL 5 megawatt wind turbine, its first power modes at both of the horizontal directions are designed to be placed in between of the 1P and 3P frequencies. And the final key point to be noted on this slide is that the stiffening or softening of the foundation can really change the natural frequencies of the tower, which can be dangerous as it is presented like this. So this is a reason why soil structure interaction should be always considered for offshore turbines, especially when nonlinear responses are expected, such as during a seismic event. So now that we have fully understood the basic characteristics of wind turbine question, we can come here to the numerical modeling process, which is done in OpenSees. So basically the modeling of the wind turbine, the supporting structure, and the soil structure interaction components follows a fairly standard approach, let's say. So the entire height of the wind turbine, 120 displacement-based beam column elements were used, and the material of the wind turbine was presented by the material of steel O2. Soil structure interaction was modeled using this Winkler type foundation with the materials of PY, TZ, and QZ. The rotor and nacelle assembly was simplified as a nodal mass at the top of the structure. And finally, the inertia of the water and the soil inside and around the transition piece and the monopile was modeled as additional mass at only degree of freedom 1 and number 2. So the modeling of tower sections is presented in this slide. Given that the tower has variable sections, patches of fibers were defined according to the actual geometry at each location. And for each cross-section, 4 fibers were defined along the wall thickness, and 100 fibers were defined around the perimeter. So with these basic modeling aspects settled, here is a comparison of natural frequencies of our model from OpenSees to some other models presented in past papers. So these results are for the same wind turbine, the NREL 5 megawatt wind turbine, on similar site conditions. So with this comparison, we thought that the modeling process of our wind turbine was generally acceptable in terms of the computed natural frequencies of the first 7 modes. The modeling of damping now is greatly simplified in our models, in line with many of the previous studies. So obviously we have noted that in reality, damping comes from various sources, and the instantaneous value of damping of wind turbine can be highly dependent on its state. So on the right-hand side here, we have a figure showing the damping ratio of different modes with respect to different levels of wind speed. So the first thing we'll be noticing is that the damping values are highly different for different vibration modes. And secondly, even for the same mode, the value of damping is also not constant. It's dependent on various wind speeds. We also have 2 figures here on the left-hand side showing the mode shapes of the 2 first tower modes on the 2 horizontal directions of the wind turbine. So one is the side-to-side mode, and the other is what's called the fore-aft mode. It is clear that the significant drag from the air has contributed a lot to the high damping value of the wind turbine at this particular direction, as shown here. So given the degree of simplification in other aspects of our fragility assessment oriented numerical model, we have chosen to use a 3% of Rayleigh damping in line with some of the previous studies. Here, the process of modeling wind and wave loads is shown in this flowchart. So we had basically 2 models for each combination of wind and wave excitations, one model in OpenFAST software and the other model in OpenSees. So OpenFAST is an aero-hydro-servo-elastic simulator, which does not simulate the nonlinear response of the structure, the soil structure interaction, nor the ground motion excitation. So it has to be used. So basically, we've decided to use it in conjunction with the OpenSees. So basically, from the beginning, the user-defined wind and wave loads were firstly analyzed in this OpenSees software to obtain time histories of the total rotor thrust and hydraulic loads. These time histories were then scaled and adjusted to be used as inputs in OpenSees. And after that, the responses from the OpenSees model were individually compared against those obtained from the OpenFAST model through this iterative process. And finally, once these 2 responses from 2 different models have agreed, the time histories that's used for the last OpenSees model were considered to be ready for the upcoming fragility analysis. So for earthquake loading, ground motion selection was performed to obtain an ensemble of 300 ground motions in total. So a number of selection criteria were followed. And the main purpose was to include as many types of ground motions as possible, also to include as many seismological features as possible as well. So for limit states, 4 criteria have been followed: 2 for the serviceability limit state, the SLS, and 2 for the ultimate limit state, the ULS. So structural performance was defined as the demand over capacity ratio, Y, for each of the criterion. And for each of the criterion, failure happens when the value of Y is larger than 1. For the SLS, we have allowed limited structural tilt and limited acceleration at the top of the wind turbine. So for ULS, we checked for both the von Mises stress and we checked for local buckling according to Eurocode 3. The calculation of von Mises stress is given in this slide. So the Mises stress is a combination of the so-called meridional stress, sigma, and the in-plane shear stress of tau. The sigma was monitored at 8 evenly distributed locations for every cross-section of the tower of the wind turbine. And that's obtained from the OpenSees command of recorder element fiber stress. On the other hand, the quantities necessary for the calculation of the in-plane shear stress tau can be obtained from the OpenSees command of recorder element forces. Now, the calculation of buckling strength verification is quite similar to the Mises stress. So this equation was directly adopted from the Eurocode 3, and you may see that it has a formulation of demand over capacity for both the sigma and the tau. The two components are then also combined by these so-called buckling interaction parameters. And again, the quantities needed for the calculation of sigma and tau are identical to those presented in the previous slide. So here is an illustration of the stress strain responses checked along the entire elevation of the wind turbine. So from bottom to top. Basically, well, for the tower segment where failure has been detected, substantial nonlinear behavior can be found in these relationships. And here is an illustration of the sigma, the meridional stress sigma, checked at 8 different locations around a cross section. So here we demonstrate the effect with a strong pulse excitation. You may see that the responses at locations far away from this neutral axis were pretty nonlinear, whereas the responses close to the neutral axis remained linear elastic. So now that we are happy with our individual OpenSees models, we start to include the consideration for uncertainties. So model uncertainties were considered by introducing these random variables when defining a total of 300 dynamic analyses for our work. So for wind, we have the random variable to control the long-term variability of wind speed. We also have the variable to control the short-term variable speed for the wind, which is the fluctuation of wind speed during the time of a single ground motion excitation. And for wave load, the story was quite similar to wind. For structural properties, we had 3 random variables, namely the wall thickness, the yield strength of steel, and the elastic modulus of steel. For soil properties, we had the unit weight of soil, the friction angle, and the shear modulus. And finally, for earthquakes, we have considered the direction of the strong components of all of the ground motion records. And here, the implementation of generating 300 samples is presented. So the implementation was done in MATLAB with a technique called the Latin hypercube sampling. The purpose of Latin hypercube sampling was to allow 300 samples to be generated for these 9 random variables, and each prescribed with a probabilistic distribution. So in these figures, the orange curves represent the targeted distribution for each of the variables. The dashed lines marks the nominal value for each random variable. And finally, the blue beams represent the actual generated 300 samples. The second purpose of Latin hypercube sampling was to have control over the correlation between generated variables. So the top table here shows the targeted correlation matrix of the 9 random variables. So basically, we expect no correlation whatsoever between all of these variables, except for the magnitudes of wind and waves, as shown in the right-hand side figure. And the table below shows the actual or the generated correlation matrix for 300 samples. So given the limited number of cases, these values are considered to be quite satisfactory. So once the 300 samples were fully generated, dynamic analysis can be performed for each one of them. And we're going to have results in terms of the demand over capacity ratio of Y for different limit states. So these results were then had to be processed by these 5 regression approaches listed here. So we have the linear regression model, the LR, the generalized linear model, the GLM method, the polynomial regression model, the PR, and the Gaussian Process Regression, the GPR model, and finally what we called as the Roda-Strauss approach, which is just a reference. So at this point, the combination of intensity measures we've used was the first node spectral acceleration of this wind turbine for the ground motions and average wind speed for the wind. Now, the first method is the standard approach for deriving fragility, which is the linear regression method. So it's pretty straightforward. For a given data set, which is, for our case, the observation of 300 wide and their corresponding intensity measures, a flat plane described by this linear equation can be fitted for these data, and the fitted surface would be associated to the information of the logarithmic mean of mu and logarithmic standard deviation of beta at each point on the surface. So then fragility can be calculated based on the standard equation. The second method is called the generalized linear model, or the GLM model. So it is an extended linear regression approach that allows for the modeling of bounded variables whose regression errors do not follow normal distribution. So basically, there are 3 key components for the GLM method. The first is a data set that follows any exponential family of distribution. So for our case, this data follows a binomial distribution, as we have divided these uppercase Y data into lowercase y data. So where 0 represents a safe structure and 1 represents an unsafe or a failed structure. The second component of the GLM method is a linear predictor. So it has a formulation that's identical to the linear regression model that we've just seen. And the third component is an appropriately selected link function. The link function modifies the prediction made by the linear predictor so that the new prediction is correctly related to this binomial distributed data for our case. Basically, once these coefficients of the GLM method, the 3 betas, can be estimated, the linear prediction will be modified by this link function. And now the new prediction is the expectation of the lowercase y under the condition of a certain combination of inputs. So this happens to bear the exact same meaning to the fragility that we are looking for, because the definition of fragility is precisely the probability of failure under the condition of a certain combination of inputs. So here is a graphical demonstration of the GLM method, and I think it'll be much more clear for you after this. So basically, we have this data set, which the distribution error of this data set do not follow a normal distribution. So it's distributed in zeros and ones. So you see that the predictions made by a linear predictor can be inappropriate, let's say. So for example, at certain inputs, the linear predictor gives predictions either larger than 1 or smaller than 0, which doesn't make sense for our data. Now, the link function is intentionally selected and user-defined. So it is used to project this original range of linear prediction to a new range. And this new range is now suited for the binomial data, and the final prediction makes much more sense. On the other hand, the standard linear regression model can be seen as a special case of the GLM method. So the difference is that This time, the link function is the identity function. So there's no difference whatsoever before and after applying this link function. The third regression method is the polynomial regression, or the PR method. So the idea of the PR method is identical to those presented for the linear regression model. Only this time, the data will be fitted by this nonlinear polynomial equation rather than the linear equation, obviously. So the fitted surface is no longer a flat plane, but a curved surface this time. And similarly, this curved surface will be coming with the associated information of logarithmic mean, mu, and the logarithmic standard deviation, beta. So the fragility can be calculated based on this standard equation. The fourth regression method we have used is the Gaussian Process Regression, or the GPR model. So basically, it is a non-parametric kernel-based probabilistic model. Generally speaking, the GPR model is used to make new predictions for a desired range of new input vector based on an available training set. So for our case, the training set was the observation of 300 cases of WISE and their corresponding intensity measures. And the new input vector was the entire range of intensity measures where we wanted a prediction. So based on this information, the GPR model can make new predictions in terms of the expected value of the uppercase WISE as a function of the new input vector. So this unknown function here is to be estimated by the GPR algorithm, which is in MATLAB. So in the end, again, a fitted curved surface can be obtained from this algorithm, and again, associated with the information of mean and standard deviation. Therefore, the fragility can be calculated following this standard equation. The fifth method is what we call the rotor stress approach. So in this approach, the intensity measure for the wind was replaced by the magnitude of average rotor stress felt at the top of the tower. Remember that the rotor stress of the tower is not a measure of the hazard, but a measure of structural response. So therefore, it's technically not really a fragility function deriving approach, but just used as a reference. Basically, by doing so, we were excluding the dynamics of the wind turbine from our supporting structure. That is also to exclude the pitch control mechanism of the wind turbine, which happens on the blades, obviously. So the linear-based GLM method was again used for the purpose of regression. And as you can see, the regression was made this time based on the ground motion intensity, as well as the average rotor stress instead of the wind speed intensity measures. So once we have the result, slices of two-dimensional seismic fragility curves. So slices of two-dimensional seismic fragility curves were being mapped for the range of this to the entire range of wind speed by using this steady-state relationship between the rotor thrust versus the wind speed. So yeah, that's the fifth method. So here are the results calculated by our 5 regression methods. So these dashed curves on each of these plots marks a design level ground motion intensity calculated following these lines. And every single point on these solid curves have the same probability of failure to the case when the wind turbine is under the combination of a design wind speed together with a design earthquake. So it is clear that both the linear-based regression method, the linear regression model, as well as the generalized linear model, the GLM, have resulted in underfitted fragility surfaces that failed to reveal the non-monotonic nature between the wind speed and structural demand. So this phenomenon is caused by the pitch control mechanism of wind turbine, as we've discussed earlier. And for the nonlinear based regression methods, the PR method, the polynomial regression method, is found to be less acceptable because depending on the data and the order of the polynomial equation that we have used, we found that the method can sometimes really suffer from a pretty strong underfitting or overfitting. And overall, the GPR method, the Gaussian Process Regression model, was found to be the best performer. And this is the data obtained for the serviceability, let me say, the SLS. So for this data set, we've seen that the predictions made by the PR models and the GPR models were much closer. So to close our discussions on regression methods, here we have a comparison of several previously published fragility surfaces that I was able to find in literature for offshore wind turbines. So basically, we wanted to see whether these previous results had deficiencies in any ways, and if they did, whether these deficiencies were legitimate deficiencies. So for the first case, the entire range of wind speeds, operational wind speed, was examined, even if a first-order reliability method, which is linear, was used. The result was still valid because the pitch control mechanism was not considered in this study, maybe a park wind turbine. So for the second case, an operating wind turbine this time was being considered. However, because the range of examined wind speed was always below the rated wind speed of the turbine, so even if a linear regression model was being used, the result was still valid. For the third case this time, the wind speed was always higher than the rated wind speed of the turbine, so that the structural demand was expected to be monotonically decreasing with an increase of wind speed. So for this case, the use of a polynomial regression model is going to be fine because neither overfitting or underfitting will likely happen for monotonic data. And for the fourth case, the examined wind speed was entirely beyond the operational range of this wind turbine. So under such a scenario, the effect of wind on a turbine will be similar to that on a conventional structure. Therefore, the use of this linear regression formulation was valid. And finally, for our case, we have examined the entire range of operational wind speed for the turbine together with the consideration of the pitch control mechanism of the turbine. So for similar future applications, basically we suggest an advanced, but most importantly, a nonlinear based regression method to be used for the purpose of deriving offshore wind turbine fragility functions, such as the GPR model we presented here. So with the appropriate selection of the regression methods, we now further examine the impact of intensity measures. A list of commonly used intensity measures were selected as candidates for both the ground motion as well as the wind. So, and a number of intensity assessment criteria was being defined following established methods from the literature. So for single intensity measures, a standard the earthquake engineering intensity measure assessment methodology was being followed, but really be aware that this traditional method, let's say, is largely based on these parameters, which is associated to a linear regression model. And on the other hand, for combinations of wind and ground motion intensity pairs, these parameters that we have used were regression parameters that are related to the nonlinear Gaussian process regression model. So to cut it really short, I will just present the results here in terms of this table of ranked intensity measure performance. So basically for wind intensity measures, you may see that all candidates had really poor performance in terms of single intensity measure criteria. So as we've discussed in the previous slide, this was because that the single intensity measure assessment methodology was based on these criteria that use the linear regression model parameters. For combination of intensity measure pairs, we have these following findings. So number one, the intensity measure of the SMV and the VF, which is the sustained maximum velocity together with average wind speed, was found to be the best performer in terms of these criteria. Secondly, the commonly used intensity measure pair of spectral acceleration together with average wind speed was almost equally good in terms of their intensity measure performance, but we also noticed that it also has excellent interpretability with reference to many of the design codes and many of the previous papers, really. And on the other hand, third point is that other combinations of intensity measures, such as the also very frequently used PGA, peak ground acceleration, together with average wind speed, this might not be really a good choice in terms of their performance for the purpose of offshoring turbine fragilities, obviously. So as a future recommendation, we suggest to use either just the standard spectral acceleration together with average wind speed, or to replace this spectral acceleration with a velocity-based intensity measure of ground motions for better performance. So now that we have finally completed our assessment for multi-hazard fragility, so I'll be presenting this very quick application for aging offshore wind turbines. So the modeling of aging in our case involved two aspects, namely the long-term foundation scour and tower corrosion. So firstly, foundation scour was modeled in our Winkler type model as this embedment reduction. So soil springs were being removed close to the, well, gradually being removed close to the surface of the soil, which is the seabed. On the other hand, corrosion was modeled as a uniform reduction of wall thickness. So the rate of this wall thickness reduction was considered by corrosion models, which is the relationship between corrosion depth versus time. And different corrosion models needs to be assigned for different corrosion zones. So basically it's a different areas of the marine structure depending on the elevation, as illustrated in these figures. So for our case, a linear corrosion model was assigned for the atmospheric zone, the immersion zone, as well as the subsoil zone. Whereas a corrosion model that follows the shape of a Weibull cumulative distribution function was used for the splash zone, as well as the tidal zone. In a similar way, a scour model was defined following a mainstream offshore wind turbine design code. So some of these parameters that controls the model of corrosion and the model of scour was defined as random variables in order to consider for their uncertainties. Now, given these figures, these curves, the wind turbine was being defined at 9 different time frames, ranging from 0 to 40 years with this 5-year interval. So for model characteristics, the evolution of natural frequencies and the evolution of mass participation factors for this wind turbine from 0 to 40 years is presented in these figures. And additional model uncertainties involving aging were being considered by introducing these additional random variables for both scour and corrosion. So based on these assumed nominal values, their distribution can be defined according to the findings from previous studies. And as we've discussed, the calculation of fragility was being performed with being repeated for 9 times over over the period of 0 to 40 years. And here are the results. So basically, it seems that based on our modeling assumptions, the rate of fragility degradation was obviously time dependent. And secondly, the change of the probability of failure at different locations on these surfaces was different. So it was most noticeable for inputs around the design level ground motion intensity measure, the design level ground motion intensity in combination with medium to high levels of wind speeds. So finally, the conclusion. Based on these experiences that we've gained from our work, a number of comments can be made. So firstly, the procedures of deriving fragility. So in this procedure, can we improve our numerical models to allow for consideration of a fully coupled aerostructural analysis? And second, as we have treated some of our model parameters as random variables, can we improve the quality of this process by using field observations or experimental data that is dedicated for offshore wind turbines rather than for other types of marine structures or even for cargo ships? And thirdly, apart from what we have already considered for the aging aspects of the wind turbine, can we model explicitly, which is very important, the short-term and long-term degradation or densification of soil due to strong ground motion excitation or operational level wind and wave loads? So basically, these questions are really difficult to be answered without the support from let's say the other end of the spectrum, which is the field and experimental investigations. So high quality data from either structural health monitoring of actual wind turbines or laboratory experiments can really help us to verify existing models, to calibrate new models, and to provide valuable references to both academic research and construction practices. So for that, our research group at Bristol is currently conceptualizing this large-scale hybrid simulation campaign for offshore wind turbines. So the reason for using hybrid simulation is twofold. So first, basically the analysis of the wind turbine action as well as the structural responses needs to be two-way coupled as how they are in real life. And second, it is generally considered to be not possible to scale the turbine rotor in laboratory so to generate realistic loads because there are significant difficulties in the scaling of the aerodynamics of the rotor and the control mechanisms, and at the same time to maintain a proper scaling for the other aspects of the problem, such as the tower, the monopile, and the soil, etc. So this experiment is currently under active preparation, and I believe a proposal has already submitted. And of course, before the implementation of this actual hybrid simulation, this configuration will really be first verified in both small scale and also under numerical environment. So this is the substructuring scheme for the corresponding numerical multi-platform analysis. So essentially, the supporting tower, the foundation, and the soil can be modeled in OpenSees. And for each step of calculation, the integration algorithm in OpenSees will be calculating for the motions at all of these interfacing degree of freedoms. This information will be passed to the second numerical substructure on the right-hand side for the calculation of accurate wind and wave loads. And the wind and wave loads will then go back to the OpenSees model for the calculation of the next step. So this is the basic principles of hybrid simulation or numerical multi-platform analysis. And we really expect to, well, looking forward to start working on this pretty soon. So this is the end. And these are the other investigators of this work. They are Dr. Rafael Durisi and Professor Anastasios Sexos. So thanks for watching.
Cool. Thanks, Zhilang. Thanks for the presentation. And we are open for questions, like any questions from anyone in the audience. They usually take some time to start asking questions. So, I mean, I will start asking. So
thanks very much.
Follow
Thanks
up.
very much.
So first thing is, like, I mean, I don't have too much idea about the offshore wind turbines, but few months back we had like another presentation on the numerical modeling of soil for offshore modeling, and there they raised an interesting point of soil ratcheting effects. So, and that apparently has a significant effect on the response of the offshore wind turbines performance. So did you consider any of those those long-term, especially when you're considering corrosion and all these, which are long-term effects? So did you also consider the soil ratcheting or all those kind of things?
Well, as we said, the modeling of soil structure interaction was basically a pretty standard variation of OpenSees modeling that you would really expect from even an OpenSees example. So that's pretty standard, I should say. But consider the fact that it is the fragility analysis that we were interested in. So we think that the degree of simplification was valid for this application.
No, yeah, but like I was just curious how much of an effect, because before doing the fragility analysis, you also have the models calibrated, right?
Yeah.
On the performance of those calibrated models, how much do you think would have the soil ratcheting effect and all those things would have? I mean, because like especially it's offshore wind, it will undergo millions of cycles, right?
No, that's not considered. That's basically not considered. That is
that's why
basically modeling explicitly for the degradation of soil, which is what we are unable to do at the moment.
Okay.
Basically, you are saying such as the use of maybe a bulk type of soil screen that's used to replace the PY springs and to model the degradation explicitly. Yes. That's not we have looked into this aspect, but I think no meaningful results has been derived because we are unable to calibrate these models. These models are really difficult to be calibrated, and more importantly, we don't have the data. We didn't find any data for that. Yeah.
That I was about to ask that question, but you mentioned it in the slide, so it's And coming to the other thing, couple of questions I have is, you're modeling, from my understanding, you're modeling the earthquake loading and wind loading combinations together, right?
That's true.
So usually my understanding is when you are in the middle of an offshore, or like in middle of a sea or an ocean, when there is an earthquake happening, there is usually accompanied with tsunamis, right?
Yes.
So, and that's a big, huge loading too. So like, So
yes, as you've mentioned it, I have actually seen one paper discussing this particular issue. And their finding was that the huge wave caused by the tsunami is typically several hours behind the earthquake. So in this, in our work, this herein, we are not really considering this. Yes, but there are definitely other works that considering both the tsunami, the wave load from the tsunami, which is substantial, in combination with the wind, with the storm, with a tropical typhoon or something. Yeah.
Okay, makes sense. I mean, I was just curious if that is something going on. And
your thinking is really correct. Yeah, there are these papers.
Okay. And before me asking further questions, does anyone have any other questions?
Hello, may I ask a question?
Yeah, sure, go for it.
Thank you for the presentation, perfect research. I have actually 2 or 3 questions. First of all, I think you performed your fragility analysis using nonlinear time story analysis. Yes, true.
Yeah.
What about IDA analysis? Do you think it's possible, it's feasible to perform IDA analysis for this much in terms of computational time, I mean?
Okay, so the computational time for 300. So you mean when I say, of course, you see that we have all these processes ahead of the actual time for the OpenSees model, but for only the OpenSees model, on a pretty high-end desktop computer for these 300 analysis, I think it takes about 1 day.
Yes, thank you. And you obtain fragility surface in terms of wind load and earthquake intensity measure, I think. What about wave load or wave height, I mean?
Right. So the magnitude of wave load is insignificant as compared to wind loads, I believe. Therefore, the main concentration of our work has been focused on wind, as well as earthquake, in line with many of the previous studies, as you can see here. So there are, except for this case is for wave and wind, and all of these are for earthquakes and wind. So
Okay.
I'm not sure if it's a satisfactory answer for you.
I think it's site specific. Am I true?
Sorry? Can you please repeat?
In some location, it might be a stronger wave load that governs the fragility surface.
Well, yeah, of course. But in case of a stronger wave, normally it will be associated to a stronger wind, because of the correlation between wind and wave load. So it's definitely, well, if you're interested, you are free to use a wave as a third intensity measure for the hazard, but then the fragility will be difficult to express, like graphically, I guess. But well, maybe you can look into this in the future.
Yes, thank you. And about corrosion modeling, what or which model you use for corrosion? I mean, you use Melcher's multi-phase model or anything else? No,
not really, because you see that the modeling of our structure is basically a beam. So it's not possible to implement sophisticated, and it's not necessary to implement sophisticated corrosion model given all these assumptions that we had ahead. So basically, the modeling is just a uniform corrosion model. But again, the uniform corrosion was observed on actual wind turbines from this paper, if you're interested. So it's not just any assumption. It has some references. Yeah, uniform corrosion of the tower.
And about, I think you mean corrosion loss in terms of cross-sectional area, loss of cross-sectional area,
can you please repeat? It's not very clear, sorry. Yeah.
How can you apply the uniform corrosion model to the OpenSees model?
All right. So the uniform corrosion model is applied as a uniform reduction of the tower section according to these divisions of zones. So basically, you know that for fiber sections, you have this definition of internal radius and external radius, and you just reduce the external radius. That's that simple.
Mhm. And my last question, which environmental load is combined with earthquake? I mean, you use operational day-to-day wind or parked or shut down turbine, or do you have any study about different position in terms of wind load?
No. So it's just a standard, like non-uniform definition of wind and wave load that you will expect from OpenFAST if you have any idea of the model. But we have not considered for the emergency shutdown of the wind turbine. No.
Mm-hmm. Okay, thank you very much. Perfect.
Thanks for your
research.
questions. Thanks for your questions.
I think there was a hand raised by Julian. You can you can go for your question.
Okay, thanks. Well, thanks for the great explanation. And well, I was wondering about the case that Pavan said. In the case of tsunami, how could you model this kind of structures? Well, in the country Peru, there are the central part of Peru is a tsunami-prone area, and after an earthquake, big earthquake, of course, we expect a tsunami in 20 minutes or so. So I was wondering, how could we model this kind of structures against tsunami? How could you model or plan?
All right. So for tsunamis, well, I think if you're going to conduct a very similar fragility analysis, then I think the modeling of the structure itself will not be very different from what I did here. However, because the magnitude of a wind load for tsunami is substantially larger than obviously the operational wind and wave loads, therefore, I think this modeling of loads is going to be different from what I did here. So the OpenFAST, I think I had some difficulties when I tried to input really high wind loads. So maybe you just use a user-defined, like uncoupled wave loads from a tsunami and apply to OpenSees. But yeah, that's basically what I can solve. Basically, I'm not being very helpful here, but I'm sorry. I don't really have much experience for tsunami, but I do have some papers. If you're interested, you can email me maybe. Yeah.
Okay. Thanks a lot.
Sorry.
Okay. Thanks a lot.
Any other questions? Okay, then I'll ask a couple more. So, right. Sorry. When you were showing that correlation table in slide 26.
Slide 26.
Yeah.
Yeah.
So I was just, it's just a curious thing. The earthquake and the soil properties usually are correlated a little, right? Because liquefaction occurs and the soil stiffness changes.
That's quite deep. Yes.
So how is it not related here?
So obviously that the wave and wind is a very direct correlation between each other.
Yes.
But yeah, for the scope of our study here, we didn't consider for the correlation between soil properties and earthquakes. It's simple as that. We didn't have the consideration because, and on the other hand, the selection criteria of our earthquakes. God, where is it? The selection of ground motions were basically intended to cover as a wide range as possible different types of earthquakes, different types of seismological features, different types that, right, just, yeah, you understand, like different levels of spectral acceleration. The purpose, it was to introduce as many as the variability as possible. So yeah, unfortunately, we didn't consider what you have said in our study. Yeah,
I was just curious. And yeah, coming to the OpenSees, this thing, you were calculating the torsion and shear in the sections, right?
What?
You were calculating torsion and shear of sections, right? So I was wondering, how did you introduce like the torsional stiffness and or like the modulus and the shear modulus? Is it like linear, or is it like you use like a non-linear? How did you, I mean, you are using fiber section, so you must be using aggregators and stuff for the shear and torsion.
Yeah, we were using a nonlinear steel material, the steel O2 model.
Yes. So, yes, but that doesn't have shear and torsion included within that.
Oh, the torsion is elastic. So it's the single value of elastic torsion defined for the cross section. Yeah.
And even for shear too, like a straight line, linear. Okay. And is it true for higher cases? Because like I don't know how things work with the offshore wind turbine, but like within the load ranges you are working, is that like an acceptable assumption?
Yes. In fact, for pure operational wind and wave loads, it is expected to be fully elastic, and even for pretty high wind and wave loads, is well expected to be remain linear. This is the reason why the specialized software of OpenFAST only supports linear elastic structural analysis. I guess, yeah. All right.
Cool. Any other questions from anyone? Then I have a couple more to ask then. So I mean, I didn't understand like complete picture of like how that regression analysis and all. It was too quick and it's too complex to understand in one session, I know. But like you talked about the GPR method, right? Like GPR analysis. And how is that from machine learning? Well, pretty much the same, right? That's how you calculate the coefficients of the data fitting and all that stuff.
The actual implementation of this model is unbelievably simple. You just use this regression learner app from MATLAB with the associated functions. Yeah.
So it's the same thing as machine learning, right? If I'm understanding.
Yes, I think behind the scene, a machine learning is going on, but we don't have to worry about that.
Okay.
Yeah.
Just wanted to make sure if I was understanding properly.
Oh yeah.
And so the other one is, again coming to the modeling, how are the earthquakes applied? Is it like applied as uniform excitation, or is it applied and how is the wind load applied along the length of the pile, or like at one point, or like how is that loading applied?
So basically, I'm just taking this figure here for illustration. So basically, the earthquake, well, it's just records, but the direction of the strong component, or maybe just X component of the ground motion was considered as a random variable, and the direction of the input was adjusted accordingly. So from 0 to 360 degrees.
I'm not asking about the direction. I'm asking about the way you applied it into the OpenSees model. So you can apply either uniform excitation or multi-support excitation, right?
Multi-support excitation. Yeah.
So why not like uniform excitation? Why did you use multi-support?
Well, that's a very interesting one, because the model didn't converge for me for uniform excitation. Yeah, that's pretty strange. And also I have encountered several issues with the system, the system thing in OpenSees, and also several other. I have to adjust between the different types of available options to make these models to converge finally. Yeah.
Because multi-support excitation doesn't make sense in this case because the loading is applied entirely along the fixed end support, right?
It's just being applied for fixed nodes.
Oh, for all the fixed nodes, but you applied
for
like
all the fixed nodes, which represents the soil.
Okay. Yeah. So then it's technically uniform excitation then.
Yeah.
Okay. And what about the wind load? Did you apply along the length of the?
So yeah, the wind loads along the length of the tower, the magnitude is significantly lower than the concentrated force of the turbine. So it is a predetermined, uncoupled a series of distributed loads.
Okay.
Yeah.
And how efficiently, like these, for example, you said like this is for a 5 meter or 4 meter diameter or 4 megawatt wind turbine, right? Like
5 megawatt.
5 megawatt. Yeah. Sorry. And how efficiently, you said like there are a lot of scaling problems, right? So this results are just applicable for the 5 megawatt and cannot be,
well, the scaling doesn't matter for numerical analysis, right? Because in the numerical models, it's all full size. So the scaling is only concerned with the experiment, which we haven't done yet.
No,
but the fragility is not important actually. The result is just a result with all of these assumptions made, but the method, right?
My question was like when you are in the numerical model, when you are making from 5 megawatt to 10 megawatt, do you have to consider? Are you considering the scaling effects by introducing some stuff, some other parameters,
don't
or
have
like?
To.
Okay.
Why you have to do that?
Because like you said, like the scaling is not linear, right? So that's why I was curious.
The scaling is not linear. Do you mean? This?
So the loading on 5 megawatt wind turbine, when I make it to double the size, let's say it's like 1 meter diameter. If I'm making it 2 meter diameter, it's not linear, right?
Then you will be needing to redefine your models entirely.
Yes. Okay.
Yeah. Obviously. Yes.
Okay.
Yeah.
Okay. And one last question from my side. So you showed the modes of side-by-side and fore-aft mode. Which mode occurs first? I was just curious because they both occur at the same time, or like one occurs first and the second one?
So it just follows these figures.
No, the mode shapes. Mode shapes, I'm asking.
The mode shapes, all right.
Yeah.
The mode shapes. This?
So you were talking about you showed an animation of side-by-side mode and fore-aft
mode. The previous one.
Yes. In the early. I didn't know those are the modes for the wind turbine.
Yeah. Is this one?
Yes. So which one occurred first?
No, it's just mode shapes. So this is for the side-to-side mode.
Yes.
And this is for the fore-aft mode.
Yes, but in reality, the side-to-side one occurs like more, ahead of the forefront, because like, for example, in bridges, you have like a longitudinal direction and transverse direction modes, but depending on like your periods and stuff, which one occurs first, you can say. So
you are talking about the mass participation of these modes. So basically, which modes are more easily excited by wind?
First excited, yes.
Well, I don't know. I don't know.
Okay.
I honestly don't know. Because these are computed in OpenFAST, and in our OpenSees model, it's simplified. So obviously, basically, there is no difference between the x-axis and the y-axis. So for the OpenFAST, I have no idea.
Okay. I was just curious because I didn't know. So okay, cool.
All right.
That's it from my end. I don't have any questions. If anyone has any questions. looks like no questions.
Okay.
I think this is the end then. Thank you, Zhilang, for your presentation and patiently answering all the questions. It was really
Thanks,
interesting
Pavan.
and a lot of things, interesting things you did there. So I'm sure like it will help people who are planning to work in this area in future. So thank you again.
Thank you, Pavan. The pleasure
Yeah.
is really mine. Thanks.
Yeah, thanks.
All right.
Thank you everyone for attending. Stay safe. Talk to you
All
later.
right. Bye.
Bye.